When a linear transformation acts on vectors, most of them change both their length and their direction. But a few special vectors don't. They only get stretched or shrunk. These vectors are called eigenvectors, and they reveal the hidden structure of a linear transformation. Understanding these special directions turns out to be one of the most important ideas in linear algebra. Hey, welcome back to the channel. If you're new here, I'm Oliver, a computer science student and tutor. In this video, we'll focus on an intuitive understanding of eigenvectors and eigenvalues, what they are, and why certain directions are preserved by linear transformations. The goal is to focus on geometry first and only then connect it to the algebra. Before we jump in, let me know in the comments, what linear algebra topic do you find most difficult right now? That would help me a lot to decide what to cover next. First, let's take a look at what can happen. Here, I have two scenarios. In both, I have the vector 1, 1. In the first scenario, we apply the linear transformation L1. This would be equivalent to the matrix multiplication L1 times V, where V is our vector here. This L1 transforms our vector V in a way that it rotates it counterclockwise and elongates it, so stretches it. So our vector 1, 1 gets turned into negative 1/2, 2. Our second linear transformation, L2, transforms our vector 1, 1 to the vector 2, 2. In this case, we do not have a rotation, so the angle here remains the same. However, the length is doubled through the transformation L2. And this is exactly the differentiation we look at when considering eigenvalues and eigenvectors. Most vectors get rotated, but a few special ones don't. Their direction stays the same. Now, formally, algebraically, this phenomena is described by this equation. A, which is our linear transformation, so for L2 this would be the matrix L2 here. So A times V being equal to lambda times V. What this means is that when we apply the linear transformation A to our vector V, it's the same as multiplying our vector V with a lambda. And in this case, lambda is a scalar. So it's a single number, not a vector. Specifically, when we look at our example of L2, lambda would be 2. Our vector V, which in this case is 1, 1 here, gets stretched to the vector 2, 2, which is the same as 2 times the vector 1, 1. So for L2, with our vector V, so 1, 1, our lambda is equal to 2. And it's important for this equation that our V is non-zero, because in that case, this equation would hold for every lambda. Now specifically, vectors that satisfy this equation are called eigenvectors. And lambda tells us how much the vector is stretched or shrunk. And this value is called the eigenvalue. So formally, one would say V is an eigenvector to the eigenvalue lambda of our linear transformation A, if this equation holds. So why does this happen? Well, first, let's look at the case where we have a unit circle. This means that we have the set of vectors which have the distance 1 from the origin. This would, for example, be the point 1, 0, but also 0, 1, which is up here. And then every single point in here which has distance 1 to the origin. And this is an infinite number of points. And when we apply our linear transformation L to it, it modifies the circle dependent on the specific transformation. So for example, the 0 matrix, which just has zeros, multiplying any vector with it just gives us the origin, so this point here. So that's one way a linear transformation can transform our unit circle. Another one would be for it to squash dimensions. So for example, this y dimension would be completely disregarded. That would turn our unit circle into a line like this, where all the output vectors lie on this line. Now, we're only going to look at those that do not squash dimensions. So linear transformations which do not zero a dimension like I've just shown with the zero matrix or the transformation which disregards a dimension. In that case, our linear transformation turns our unit circle into an ellipse. The reason that it does not turn our unit circle into a more complicated shape is because linear transformations cannot bend space. They can only stretch and combine straight directions. So every line stays a line, and every point on a circle is built from these straight directions, which are only stretched and combined. Now, I will not get into the specifics here, but because in our linear transformation we only stretch and combine straight lines, one possible outcome is that if you stretch certain directions more than others, the only possible outcome of transforming a unit circle is to transform it in an ellipse. So the cause is the linearity, and the consequence is an ellipse. In certain cases, this implies that specific directions are preserved. So when our stretching happens without rotating, the preserved directions become visible as eigendirections. And when I speak about eigendirections, it's just the direction an eigenvector goes in. So for example, in this case where this vector is transformed into this one, it stretches our vector of length 1 from this one to this one, but along the same direction, we can take any vector. So for example, this one, going in the same direction but having half the length, would also be stretched into the same direction, but just land half the distance. So have half the length of the previous vector. Now there's also the term eigenroom, and this defines all vectors that point in the same eigendirection. I've said that this vector is an eigenvector, and all vectors that lie along this direction, so these, they build an eigenroom. Now this line would go on infinitely, and it's a line through the origin, so it's a subspace of our two-dimensional space. So once we have the eigendirection, we don't just get one vector, but a line. And in some cases, even higher dimensional hyperplanes. So that's just what I mean when I say eigendirection and eigenroom. So this vector gets stretched in this direction where the angle or the direction does not change of our original vector, thereby making it an eigenvector. This would not, for example, be the case for this vector here, which lies halfway in between the green and the orange vector, because now halfway between them is no longer on our y-axis. So this vector gets stretched into this one here, but no longer has the same direction as it had before. But for our orange and green vectors, which the direction remains the same for, these are eigenvectors, defining eigendirections. This does not always have to happen, specifically when we have rotations. So for example, looking at the same vectors as in the top case, in this case, we have that the transformation also defines a rotation. So this vector is turned into this one and this one into this. So we're rotating clockwise, no longer preserving the direction. Next, we'll look at some lightweight examples to show how you can recognize eigenvalues for simple matrices. Now the first one is a diagonal matrix. Here, we only have values along the diagonal, and all other values are 0. We can, from this matrix, which defines a linear transformation, read out its eigenvalues, which are, along the diagonal, 2 and 1. And you can see if I multiply it with a vector 1, 0, we get 2 times 1 plus 0 times 0, so 2 in the first entry, and in the second entry, 0, 1 times 1, 0 is 0. So 2, 0. If we pull out the scalar 2, we exactly get this form of the eigenvalues. Namely that our eigenvalue 2 has the eigenvector 1, 0. So our linear transformation times the eigenvector 1, 0 is equal to the eigenvalue 2 multiplied by the eigenvector. We can do the same for the vector 0, 1, where applying it to our linear transformation, we get the vector 0, 1, showing us that 1 is an eigenvalue of our linear transformation and 0, 1 is an eigenvector to this eigenvalue. We see that multiplying this vector by 2, giving us 0, 2, doing this equation again, we yield the same outcome. So this vector, 0, 2, is an eigenvector to this eigenvalue 1. So having only stretched our vector 0, 1 with the factor 2, we still get the same eigenvalue. And this is exactly where eigenroom fits in. So both of these vectors are in the same eigenroom of this eigenvalue 1. And the eigenroom of this eigenvalue 1 is a line through the origin, which is spanned by this vector 0, 1. So if you look at our space, the eigenroom which we just talked about, which is spanned by this 0, 1, is in fact this entire axis. So this would go on infinitely. This would be the eigenroom to the value 1. And then the eigenroom to the eigenvalue 2 would be spanned by this vector here, 1, 0. So it would run orthogonal to this previous eigenvector or eigenroom which we defined. So what this tells us is that the linear transformation defines a scaling of our x-axis by 2. So a point lying here would be scaled here, and a point lying here would be stretched until here. And in our y direction, it would be a scaling of 1. So we do not stretch or shrink. Our vector 0, 1 would stay our vector 0, 1. And using that information, we can tell that our linear transformation turns this circle here into this circle out here. Since it stretches in the x dimension by a factor of 2 and leaves our y dimension as is. Now we can also look at a shear matrix, where here, instead of an ellipse, I've defined 4 points that build a square. These are the 4 points and how they're transformed. So they result in this output. What we notice is that this vector gets rotated, this one also gets rotated, and that's also true for these other 2 vectors. But what we can also see is that the midpoint between these 2 vectors, so this point here, gets transformed into this vector here. So the same point. It's also the midpoint between these 2 vectors. And in fact, this is true for all vectors that lie on this x-axis. If we multiply this with the vector x0, where x is just a variable, our result is x and then 0 as the output. So, in fact, all our points which lie on this x-axis get scaled by a factor of 1. Their direction remains the same, and their length too. So the x-axis is an eigendirection of this shear matrix with eigenvalue 1. Everything not on the x-axis is tilted into a different direction. They do not land on the line defined by the original vector, which we can see by these points here. But also, for example, this one getting transformed into this one into this one, and so on. The conclusion from this is that we only have one eigendirection. So what we learn from this is that eigendirections don't always have to come in neat pairs. There sometimes is only just a single preserved direction. And in fact, if we look at just a rotational transformation, so one which just rotates our matrix, say, 90 degrees clockwise, this matrix has no eigenvalues, no eigendirections, because every vector is rotated, so its direction changes, and therefore is not an eigenvector. If you'd like a geometric introduction to linear transformations, you can watch that video here. And if you're looking for short intuition-first explanations of other linear algebra topics, the full Linear Algebra Basics playlist is linked here. If these videos are helpful, feel free to subscribe for more. And as always, thanks for watching.